Okay, let's move on. Okay, so congestion maps is the way the tool lets you know which area where congestion is. By looking at congestion map, you know where congestion is and where to resolve them. So here's just example. These are here, this area here light up. So this is the legend, meaning that one, this is severity. So this is one 0, 1, 2, 3. So there's 7 tracks over. Basically, what it means is this red, I mean, it is short of 6 tracks. So you can see this area is congested here, so on in this side. And you can define these. You can change the color if you want to, but these are just default colors it showed up. Okay. So this is, and you already know about this. There's report congestion. That's overflow report congestion. That hotspot. Okay, so in the lab, you'll get to play with these, how to display congestion and how to go about fixing them. So the tool will help you, right? The tool will help you display the congestion where it is, and you can zoom in and in this area, for example, I zoom in this particular G set, right? You can see here, I actually take this one. This is vertical congestion, it said V, so it needed 20 track. This is the number needed, and this is number 17 is the number of availability. So they need 20. So this is 3 over. So this is the green area. So you see the red is 22 or 17, so 5 over. It's short fives. So you can zoom in and tell the overflow, the lack of resource. Okay. In lab 2, you get to play with this. Okay, congestion map score. I think in one of the lecture we talk about this. So the overflow is horizontal versus vertical score. It goes from 0 to 100%. So the lower number is the better, which means less congestions. The higher the overflow, bad, meaning more congestions. Okay, so usually in Innovus, anything I've seen, if it's over 1%, it's going to be a little more challenging to route. So you have 5% congestion. It's all highlighted red. You got issue. So anything 1% or less usually is routable, but anything over, it's going to be more difficult. Uh, okay. In terms of hotspot score, hotspot basically highlight a certain region that had local hotspot, meaning the congestion score. It's just another way of showing this. Okay, the lower the better, the higher the more congestion. So anything over 100 usually is not routable. So these things pretty much correlated. So here in Innovus, you can do report congestion outflow, and it'll show you overflow, and then it show you the horizontal congestion versus vertical. So this one say 0.72% horizontal. I mean, it's okay. Vertical congestion is 2.3. It's too high. It's greater than 1. So we got to go resolve this. Okay. And here, when you do hotspot, it tell you this is the box, the B box, B box, meaning this is an area, and this X1, Y1, X2, Y2 is the square. This is a hotspot score of 117. So you zoom in that area, you should see the congestions. This is the high. Yes.
Doc, we have a question that's come in. What is the CNTH and the CNTV?
Oh, this is the count, horizontal congestion count and vertical congestion count. Okay, so this is the way that Innovus score score. You can look more into the definition of it in terms of details, exactly what it meant in when you do the manual the man on the report congestion. So this one will tell you more about exactly what these numbers are. It's basically the count on the number of congestions in that particular uh, uh, percentage here. Yeah. Yeah. So the main thing from this takeaway is this percentage right here, right? And then this B box. And then you go back and look at the congestion map where they are. and then based on this, and you can determine, okay, it's severe congest. How do I move this around? How do I reduce this? Move cells apart and redo placements and whatnot. So that's the most important thing is the map, where it is in the design, and then the score, and the score here, and then what's the top, the worst area. Okay. So these are the number for Innovus tool. If you use another tool, it's going to be different. The normalization will be different. So we this class is teach based upon the Innovus. We use Innovus tool. So this is the number I've used. Okay. So if you use another tool like Synopsys, the score may be different. They normalize differently. So remember, this is Innovus score. So if you don't take this number and use it on if you happen to use another tool, it's going to be different. They normalize different tool does it differently. Just score differently. Okay. Okay, so here I just show the example of the same the same congestion area. Uh, Giving the default setting, right? You can see here you go from severe congestion, right? After you go and fix it, so it gone down here a little bit, and here's least congestions, right? So based on the default colors go from green to red. So this is very severe. This is green is less congestions here. So you can see the same area it gone down. So that's just give you a feel of if you look at the congestion map, you can tell, okay, the highlighted red is a severe area, and these are less severe, meaning that maybe one or two tracks shorts versus this maybe 5 or 6 tracks shorts, meaning that you need 5 or 6 tracks to your finish. Okay, so why do we have congestions? What are the costs? Okay, so first thing is related to density, right? If you have a lot in one area, then you're gonna have congestions, right? So basically, it's very dense, too dense. And also the other one is high density pin counts. So you have a lot of cells like inverter, or those are like 2 pins. If you have like flip-flop or AOI super gates that have a lot more pins. So those are higher density pin counts. So higher pin counts, meaning you're going to have more nets, more track to route through those pins. So that's going to result in higher density, higher congestions. And then the other ones you have standard cell new macro. So in this area here, right? You have too many density cells near here because what happened is the macros here, the memory going to have a signal going out, right? Going out, and therefore is take up some of the tracks. So you can a lot of time you want to put the halo. We talk about halo is the hard pockets extended further out to keep it away. If that's not enough, then you gotta do some um, use some strategy to move the cells out. Okay, it's also high density high pin density at the edge of macro. Same thing when the edge of macro. Usually, a lot of time the issue is gonna be around macro here, right in here, and then a poor floor plan. So a lot of time, I think we talk about it. If you in the standard cell, you want the square, open air square like this. If you have a shape like an L shape like this, or some little shape that are not square, are not rectangle, you have a lot of cut in and out with a macro, then you're going to have more likely to have congestion. In the next slides or two, I'll have a example what that look like, and you see what I'm talking about. Or a poor synthesis. Okay, a poor synthesis, meaning that so when you get an RTL, right, you synthesize it to a technology. So what happened is the synthesis did a poor job based on so a poor job meaning that the timing is way off versus what the placement timing is. So you're going to have a lot of after place opt, you're going to have add a lot of cells, add a lot of buffers in, and therefore just to meet timing, then you add a lot of cell, then the floor plan ready to handle the size, then you're gonna there's too congested, right? The density is too high, then you may have to go back and expand your expand the size of the chip. And the other one is poor PG strategy. PG standing for power and ground. So in the floor planning stage, you learn to add, we add the power ring and power stripes. So what I mean here is poor strategy, meaning that sometimes you add too many stripes than it's really need, then you take up too many tracks for that area, and therefore you don't have enough tracks for the signals to route. So sometimes that can happen. So if you over design your power grid to meet the IR drop and EM, then you might take up more tracks than really needed. Therefore, it can create congestions. So those are the things that I can think of that cause congestions. Okay. Any comments or questions about what is congestion and the cost of congestions before we go to the next topics? Let's see, Phil and Ting here. You guys have any inputs?
We have a question from Leitan Chung. Is there any way we know we have over-designed before this step?
Is there where we over design? So over design, assuming you talk about over design in terms of the size of the estimate. So in my experience, usually if you do a chip in design, they kind of know already because you remember we talked about the size of the per technology. They know the density per square millimeter, how many cells you can pack in there, right? So based on that, they kind of have an estimate. There are sometimes what happens, you can miss the estimate, right? You can miss it, and then it become too dense, and you have to go back. So usually, initial floor plan, it usually is 90% accurate in my experience. There's 10% chance you go back after replacement. You go back, you have to expand your chips, or you shrink it if it's like for that technology a number of metal layers. You can either shrink it if you, for example, if that particular type of design and technology, if you can route at 70%, okay, then that's the target. But if you coming in at 80%, then okay, you're too high, then you got to back out and grow it to where the floor plan is 70% utilization or density. The other way around, if you come in at 50%, okay, then you are too big, then you come back and you shrink it to around 70. If you already know ahead of time or based on the history of what you've done before in a similar design. Okay, so that's it can happen. Okay, but at this state, you based on the technology, based on the square millimeter and based on history, if you have some history, then you can pretty much hit the size about 90% of the time. But there are times you can miss.
All right, we have another question. In the video, there are two types of congestion, placement congestion and routing. Can you tell us more about these two types and what is the cause of those two?
So placement congestion sometimes during the placement stage. So basically those two terms, sometimes people use in the placement called placement congestion. So placement congestion basically indirectly related to routing congestion, right? So placement congestion basically referring to what we talk about here. Here is in terms of this is sometimes we call placement congestion because there's really no routing here, right? So the term used placement congestion meaning that it's a high density area is congested. So in placement, sometimes people refer to that term, okay, placement congestion, but indirectly it is routing congestions, right? So in the placement state, sometimes people call it placement congestion because it's during placement, but it's basically meaning, there's too many cells in one area like this, right? So they call placement, they refer to that term, and some people call it routing congestion. But really, congestion is bottom line is routing related to tracks, number of tracks available versus number of tracks needed, right? So some people call it placement. Congestion is basically what we talk about here.
Yeah, and something to add to that is that sometimes uh, different cells have different number of pins on them. For example,
Right.
an exclusive or a complex gate, even though the cell size is small, but there are many pins on them. So while the placement density might be not as high as other, but the routing density can be very high because of number of pins. So that's why there are differentiation between routing and placement congestion, right?
Okay, so I see a question from No Taiyanhao. Can you talk more about how poor synthesis or poor PC strategy affect congestions? Okay, so I kind of touch a little bit about it. So basically, when we've heard, let's say poor synthesis, meaning that the mainly is the timing gap between so after you run synthesis, right? So in synthesis, you also have a target timing, the timing target, right? The same targets that we have throughout. So if your design is designed to run at 400 megahertz, that's your target intensity. That's going to be your target toward the end, every stage of design, right? So in synthesis, right, we learned that the standard flow synthesis is wire based. So it doesn't have any global routes that have any placement. So it's based on the number of cells and loading and so on by wire load. So it's gonna based on that, it will do bufferings and so on, right? It will add buffers and uh, things like to try to meet the timing, but it based on the wire load models. Um, so let's say if that target is hit, right? It's like you met in a synthesis, but when you go to placement and then you run your uh so you run a placement and you time it after you place, you can see there's a huge gap. I think in the lab, if you've done lab one, you should have seen, no, actually lab one, actually no, lab two, this lab, you see that after placement, if the timing gap is huge, a huge difference, 20% difference or depend on the design, the technology, the gap. And it's a huge difference and then you estimate the size that you estimate, right? You assume that it's not going to be 20%, you assume maybe 10% or 5%, but you end up at 20% or 30% difference, right? So what happened is you're going to placement based on that particular size, you estimate 10%, but then your synthesis miss or gap is 30%. Therefore, the tool will have to add a bunch more buffers to make up that 20% trying to meet target. And so you blow up your area. That means your density is too high, you move it around. The cost, you move it around. So therefore, that's what I refer is poor synthesis, right? The gap. Poor PG strategy is sometimes some designers will over design the PG. The pound guard have too many straps, vertical strap and horizontal straps. They worry about mainly, IR drops and EM on the PG nets. So they over design it. And what happened is over design, and then in the area there happen to be too many cells. And so it take up too many tracks, right? So in that case, that's what I call poor PC strategy in term from the standpoint of congestions, because you over design grid wire, you can take that away. So that is one of the things that we're going to talk about is if that's the case, then we would take away, take out, we'll trim the PG straps and make tracks available for the routers to route for the detail route for the signal nets route.
Yeah, something to add to that is typically the incoming cell utilization is kind of a number to shoot for. For example, say you want after synthesis, you have certain total cell areas, right, in the incoming netlist. So say that total cell area is certain square micron, and then you design your placement area, you know, based on the target utilization, say 70%. Right, so when you have a chip or a block floor plan with 70% coming in, and you're planning for 10% for clock trees and timing closure. So if your design is routable, say at 80%, then that works. But if coming in at 70%, but you over designing your power grid so that 70% with the tracks, like but say being covered by the PG network, then the amount of routing resources is not as as big as you think. So that means if you have too dense of a power grid, then the incoming utilization should be lower than 70% to compensate for tracks being lost by the over designing of the PG, the or pound ground grid. So everything is kind of you have figure merits, you have target utilizations, but you also have a limitation in terms of what are available in terms of routing tracks, right?
Yes, yeah. Thank you. So yeah, there's only a fixed number of routing tracks available per G cells. So those number doesn't change, right? Okay, thank you, Phil.
There are other questions you want to read, or somebody can read for you.
Okay, the congestion between the 2 micro and the picture is caused by pin density, right? I don't know. I haven't done analysis on it, but based on this, it looked like their cells probably in between or something because the pin, yeah, it could be if the pin don't line up, if they don't go straight across. For example, if the pin line up, all you do is using the horizontal track, then should be no issue. If the pin don't line up, meaning it has to go up and jog down, then the vertical track is going to be an issue. So based on this, I think most likely it's going to be the vertical track issue because you don't have that many vertical tracks here.
Yeah, and also so at the distance, right, is pin density right there.
Yeah.
But also to help with congestion, you can block the cell placement. If the cells are placed in those chimneys, we call them chimneys, right? That will magnify the congestion. So there are constraints that you can put in, say, don't put anything except buffers in there just to minimize the cells being placed in those chimneys, right? Yeah, but at the distance, these are pin density
Yeah,
problem,
they look
not cell
like pin.
utilization, right?
They look like pin density. Look like most likely going to be the vertical track, because that channel is very short, very narrow, or the chimney is
Yeah,
very narrow. And if the pin don't line up, then the route has to jog, and you're going to be short of vertical tracks. So it doesn't matter if you put blockage here and that. If you short vertical tracks, it's not going to resolve it. The only here to resolve, you got to move these to parts, or
yeah,
move it up and down the line up where the pin just goes straight across with
yeah,
the route.
exactly. That's why when you say, yeah, you have blockages, but still congestion, that's because of pin
Yeah,
congestion,
yeah,
right?
yeah.
Pin density.
Okay. Any anything else?
Very good questions.
Okay. Okay, so the next is guides to minimize congestions. Okay, so okay, I think we learned about the placement blockage, right? We talk about the hard, partial, and soft. So these are the strategy that you can use to keep the cells from being or not too many cells going to the area that congested, right? So remember the hard blockage, you can use hard blockage where you don't want any cells in there. For example, in that channels with back here that we show earlier. So if you don't want any cell there, put a hard blockage in there. But in this case, it doesn't solve the issue, right? So it depends on where it is. So you can use hard blockage, you can use soft blockage, and you can use partial blockage, right? So remember on the partial blockage, if it's too dense, you don't want too many cells in that area, you draw your square box and put a partial. If it's the current percentage is like 70 and you need is 60, then put 60 in there and they'll limit number of cells in to be 60. So that's basically keep it from too many cells to be in certain areas. So one of the ways to add different kind of blockages. Okay, the other way is creating halos around the macros, right? If the macros you might have to increase this a little bit more to create macros around to keep cell away from uh, the congested area, especially at the macros, near the macros. A lot of time around the corner here, if there's too many cell put here, there's going to be issue around this corner. So usually people will put a partial blockage if there's too many cells in there to limit the number of cells being put in this area. Okay, add cell padding. So I don't remember if we actually talked about cell padding before. But anyway, cell padding is basically is a way to pad a cell so on the around the particular macro, right? So if you know that a flip-flops that has a lot of pins and you want to reserve space around it, the right, left, and right, you can tell it, okay, do not place any cell next to it on either left or right. Either this is two unit, 3 unit, and so on either sides of the cell. So for example, let's say this is the scan flip-flop X2, right? So you pad it, you cell top right, keep it away, then they will not place cell near according to um, these numbers. I think this mean I I think this mean the right side keep two of these see this as two. So I mean it keep one of these side the same size is available. Keep that same width. I think that's what that means.
Bach, we've had a question come in about some of the information on one of the slides. It says that Halo's type is hard blockage. The slide says that Halo's type is hard blockage, but when you looked it up on the internet or watched videos related, those said that Halo's type is soft blockage. Is this a mistake in the slide or choosing the type of Halo depends?
Yeah, the halos in universe, halos gonna be hard blockage. Nothing gonna be standard cell can't go in that area. So I'm not sure what the internet saying is about it, but the halos when you extend the halo here, this area no cell's gonna go in there, so it's considered hard blockage.
So one thing to sometimes maybe it's due to different tools, or one
Right.
thing to know for sure is that you do a man page on the
Okay.
adding of placement blockages, and Katie's will
Yeah.
tell you exactly what a halo is. Right?
Yeah, a different tool may consider differently. So it's ICC may consider differently, but we're using Innovus. So this is it's going to be Innovus. Like Phil said, you want to know exactly when you do a main create halos, and it'll tell you exactly what that is, whether it's a hard or soft for your particular tools. Okay. So for Innovus, for our purpose, when you create this, it's going to be a hard block because there's no cells going to go in place in this halo area. Okay. So go back to cell padding. So this is just this is used usually for a particular cell or you want the whole region. I think in our lab, I did it for the entire everything. So just to spread out the cells because I think our design it tend to clump the lab. It tend to clump everything together very close. So I I think we look in one of the ticker script, you see where I actually spread the cell out. I think in placement in the lab, you guys just did the lab number 5. You see I use cell padding just to spread everything out. Okay.
So I want to add to that. This is one of the examples that we need to help the tool. The same way as the corner blockages on the macros, right? So you know by default behavior, the tools want to minimize the distance between cells, right? So if there are high speed requirements, they will place the cells very close together to minimize the RC, therefore speed up the circuitries. But they are congestion aware, but timing driven is very high in priorities. So if we don't give this the placer some help like this, it will bunch up things together based on the speed requirements. So high speed blocks tend to be very high in local density and therefore create some problems. So this is a very so you need to be familiar with this and use it in your real design because very often that you need it. I've seen most often used will be on flip-flops. Right, so you do a spacing around this flip-flop, that tends to solve most of your congestion problems. And in some design, like Bart mentioned, he put a spacing, the padding on everything. So it's important techniques to learn.
Okay. Thank you, Joe. Okay. Any more questions? Because the how to resolve congestion is a very important concept in placement stage. You got to learn how to resolve these congestion and make your design routable at the after placement stage. If you can't resolve this, there's no point of moving on to the next step, next stage in the flow.
Yeah, and this knowledge is critical because if you are push button kind of person, you have a congestion problem and you keep on going on and on and on, try different things, right? While just a simple cell padding would do the job and still give you time enclosure quickly. So that's why it's important to understand all the details about how the tool does its job instead of just run the command and wait for the best results.
Yeah. Yeah. So to me, in the entire PD flow is floor planning is important, but in this stage placement, this is one of the most important concept in terms of, most likely more than not, you're going to have congestion, either not overall, but some local congestion. You got to know how to resolve, how to move it around and to spread it out to resolve that. So if you don't understand something at this point, please ask questions and we'll try our best to answer your questions.
Yep, it's just not run place op, CTS op, and route op, and you're done. It's a ton of stuff that goes into the methodology that to do a good job to create a chip that that is competitive and have commercial value. You need to dig deep and have very good implementation. Otherwise, you have a chip back and you can make claims all you want, but nobody will buy your chip. It's too big, too expensive, too slow. Right?
Yeah. So yeah, so in your labs, you may have congestion and you got to know how to resolve it and so on. So I didn't that lab that purposely didn't it's not super clean for you to see what's happening and you use your skills, what you learned to resolve it in the labs. You see some of the things that I left at default and you should be able to see, oh, it shouldn't be here. If you pick up all the concept from floor planning to placement, you should be able to pick that, oh, this shouldn't be there, this could be an issue, so on. Okay.
Hey, but I have a question for you. Probably I missed it, but it seems like you're not helping the student with the lab anymore. They do on their own.
No, we have labs. We have labs. I have labs.
Oh,
I have the student. Yeah. Today we'll have it in the second half. I'll go over
oh,
the
because
yeah. Yeah.
I see. Because I attended last week and the session this week. You guys must go on for 2 hours without
Right.
lab.
So I will have two labs. So the first two lectures, the first lecture and the third lecture don't have any labs, and then the second and the fourth have labs. So you missed both of those.
Okay.
That's why.
Okay.
But I have labs. Yeah.
Okay.
Yeah. Thank
Just want to
you.
make sure they have enough help to do the lab, and then
No,
that's
plus
good.
my lab instruction. Yeah, we have lab. We'll go over the labs the second half of this.
Okay. Cool.
Yeah. Okay, cell padding. Let's move on to the next one. Change a placement strategy to congestion driven. I think this is pretty much understood from our strategy placement strategy, right? By default, it's going to be time and driven. So assuming that you do time and drivens, and then you meet timing, but then you have congestion. So first thing, easiest thing to try one of the strategies to change the congestion driven to see if it's actually going to help. Right. So here the example here. So this is time and driven, right? You can see, take a look at D and G, right? Based on congestion driven, you can see how it places have close together, trying to minimize the wire length, right? To meet timing. So if you turn it to congestion driven, the tool may do this. So you take a D and G, right? D's here. Now G is down here, so it's spread it out. So you can see here, it only need 2 horizontal track versus 3 here. So, but this come with expense, right? The expense is longer wire length. Your timing may not be met. So that just demonstrate a simple concept of congestion driven, right? You can see how it spread the cell out. Try to minimize congestions. So here the tracks is 3, here's 2, but it come with expense of longer wire length because the cell sorry spread out. Okay, so so I think this is one of the obvious strategy that we discussed, right, from time driven to congestion driven. Okay, so here we're talking about poor PG to over design the PG, the concept. So so for example, here you have 1, 2, 3, 4, 5, 6, 7, 8, right, in this particular area, and yeah, you have congestions, and so you know that your PG already meet over these. You run the IRNEM, you know that you don't need that many. So first thing you can do is you can trim it down. What I mean trim it out here is to get rid of 3, 2. You trim it down, but you still have to meet the EM and IR requirements, right? So this is what I mean by updating PG or pull PG. You can do this by trimming down to make the tracks available for the routers, for detail routings. So this usually is not the first resort that people will do. Okay, other strategy is more likely. But if they try all the different strategy and they realize, oh, the PG over, because in placement, you really haven't run IR and EM at this stage to really know, at least in most of the design that I'm involved with, okay, to know. But this is just keep in mind one of the strategy. It's not the first, second, or third option that you go to. It's probably the last resort you go to.
Yeah, I want to add to that. But we cover during floor planning, we cover early rail analysis, and it is strongly recommended the early power analysis be run to avoid over designing and to make sure if we aggressive in terms of power grid, meaning that we don't over design, then we don't under design. So the only way to be sure without having spent days and weeks on a power grid that at the end you find out IR drop is a problem it is strongly recommended that you run early rail analysis. So, but it's not something as scope of this class, but be aware of that, right?
Okay, so the other last resort is to update your plan. You really don't want to do this because that means it's going to cost you a lot of cycle time. So I think and Phil has I reused some of his pictures here on the slide. So here we're talking about if you have this pocket like this, right? This is not a good area. So you want to do replan. For example, there could be congestion here, most likely you have here. So you want to redo floor plan where you open it up, where this is more of a smooth open area. So that's a better floor plan versus you have these cave or what you call it, Phil, the called cave or this pocket area. Right. So this is a much better floor plan versus this. So you can avoid this small pocket like this, then up front because you tend usually this is going to be more likely not, tend to be the congested area. So this will be much better floor plan, right?
And you all know why, right? Because so for example, in this area, right? So um, so by the nature of the timing optimizations, if that critical paths that related to all these memories, then cells tend to be bunched up here. So they put a lot of cells near the critical path, for example. And now you have all the signals that escaping from here go down, from IO to go in, and from memory to go in. They tend to connect to the standard cell areas. So a bunch of signal going through here and go through this small area. So that means that you talk about placement density, pin pin density here. So that's why it's bunch of things happening in the area. Versus over here, you see, the cell can be put in here and signal can come out very easily. So those are notches. I think we call them notches. Right? We want to avoid them.
Okay. Okay, so let me reemphasize. This is not the if you have congestion here, I'm not suggesting you change the floor plan right away. The first thing to do is try your partial blockage and those blockages, add blockages, and also use the cell padding. Those are your first solution, and because those much easier, you just rerun your placement and then do your congestion analysis, and you see it go away. Those are much faster solution versus having to go here. So after you exhaustively try to other all the placement blockages and things like that, and change your strategy and so on, before you go back to floor planning, redo your floor plan. Okay, so you want to do other strategy, the simple one, those blockages first, right? Before you go here. So don't just go here because you see congestion and just change your floor plan right away. That's not what I'm saying. These are just a strategy, but these are after you exhaustively use the other strategy, placement, cell padding, things like that before you avert to this, because this is very costly in design cycle time, right? You go back and redo your plan and go back again.
So when you say hotspot, right?
Was that a comment or was that a question too?
Yeah, it's a question. When you say hotspot, right?
Oh,
So
yeah,
hotspot?
hotspot. Yeah, hotspot is report congestion. Yes, yeah. So it can be hotspot. Yeah, so hotspot is a congestion. Yeah. So your hotspot scores is over 100. Then you need to take a look at it. Yep. Turn into congestion map. If it's on the heated side, then you need to take a look at it, right? Okay, so one other strategy is if it's post synthesis, you want to update the physical aware. So this is kind of beyond the scope of the class, but I just want to put a slide in here to make you aware of. So traditional synthesis is non-physical aware, meaning that it uses wireless model, which I kind of mentioned earlier, right? a more advanced tool these days, they push all the physical information into synthesis, meaning that they will take the, you can have the depth go into synthesis, right? For aware, and you can recycle feedback into the synthesis tool, and they link together from placement to synthesis. So the sensor has knowledge of the placement and so on, the macro placement and all that stuff. So it knows those are the area that the physical information. So the more physical information the sensor will know, the better decision will make, right? So you can conversion your timeline much faster. So you can close that gap that I was talking about earlier, the post synthesis, the timing gap between synthesis and your placement timing. So just be aware that there's a traditional sensor flow versus a physical aware sensor flow. That's all I want to mention here, but this is kind of beyond the scope of this class. Okay, so just be aware. Okay, so that's anything until thing that I did not cover regarding the congestion strategy minimize methods.
Yeah, I like to just add one simple stuff to help people understand the need for physically aware synthesis. Can you go back to that slide? I just want to give an example. So we talk about white loop models, right? As you know, white loop models. So consider this is your floor plan, right? The white loop model is based on fan out, right? So if you have a driver that driving from this corner of the design, and you have say a memory that been placed here, which a fixed location, right? So if you base on white loop model, and this guy is only driving this one single memory, so in white loop models, a fan out of one, it give an RC of equal to a fan out one times some factors, right? And this factor depends on your size of the block that you've been analyzing. But in reality, if this is 3,000 microns away, the RC in here, the reality of the RC in here is much more than this little number. So you grossly inaccurate if you just count on the white loop model. That's why when you do a physically aware, you feed in the depth, which have this information of, hey, I am driving from a driver here, I'm traveling 3,000 micron distance, and including some of the detail planning, global route, etc. So it's much more accurate RC. Therefore, you can have timing closure a lot faster than with the white loop models. So grossly inaccurate in a lot of cases. Yeah.
Okay, thank you, Phil. Okay, so Wing Dong Wang Fuk asking, what is the flow to find out which solution should be used to resolve congestion problems? It there, I mean, it's not a flow per se. It's just a strategy. You want to try the easy solution first, meaning that you don't have to do too much work, like going back to cost you much time, cost you too much schedule slippage, right? So first thing to try is, to spread out the cells by using cell padding or
Are you on that
blockages
slide or
type.
not?
Huh? Go ahead. I think we already answered that questions, right?
Maybe Tian didn't mean to say it. Maybe, yeah.
Oh, okay. So you want to try, you want to try the strategy first right here, right? Different blockers and cell padding create halos. Depends on where the congestions is, right? If it's around here, macro around the corners, then you may want to do partial blockage. try that. All right. If it's still too many, we want to do hard blockage, just get rid of all the cells out of it. So you want to try those solutions first, or cell padding also before you, and then before you you trade for congestion driven placement before you actually go back to floor planning. So you want to try all the different blockages type first. So because those are the quickest one.
Yeah, and before you try it, I encourage you to zoom into the congested area, right? When you do a congestion analysis, you see red hot spots, right? And you go in there and you zoom in and you try to understand, is that because of these overflow on G cell? And or is that because of those pin density? Yeah, so by understanding what might be the cause of congestion will help you determine which method to use. I don't think there's something called a flow. It's
Right.
more of yeah, the flow would be understanding the nature of the congestion, and in your arsenal there are multiple ways that cover that can be used, and depending on the problem you can use you can pick and choose, right? So there's no automation here.
Yeah, so on this example, this is a good example right here, right? You can see the congestion here. And I think some of you guys said you put in blockages, it still doesn't help, right? And then you know us, yeah. So based on this, based on experience, you know that you zoom in there, it's going to tell you, you zoom this area, it's going to tell you the vertical track issue, right? You know it's lack of vertical track. So lack of vertical track, there's really not much you can do versus line up the pin, or you can move this out to create more tracks. So all the other strategies are not going to help here in this particular case, right? So you kind of understand it and feel set, and then you know what kind of solution you need. Okay, so I think that's all the congestion. I will pause here to see if anybody have any more questions about congestion before we cover the last two topics of the placement, because this is a very important concept to understand.
Perhaps we could take a short 5-minute break and come back and answer Nguyễn Lê Minh questions and go on.
Oh, it's already 10 o'clock?
Yeah.
Okay. Dave, can we take a 5 minute Bible break?
All right, we're finished with our 5-minute break.
Okay, let me go back to. Okay.
We had a question come in just before the break and also a comment from Tian. First, Tian wanted to add that on the update floor plan, it's important to spend time up front and to get the better floor plan so that you don't have to go back when it's too late. Also, you need to take into account on the design cycle when trying different strategies. A month before tape out is very different from a week before tape out. And then a question that I don't think we got to, is there something called test design where we fix the congestion problems and then we apply it on the real design, or we just fix it on the real design?
Okay, so test design are okay, so there's the test design would be different. There is a test design, but usually it's for testing a new because test chip. Usually it's testing for when you do a brand new technology. So for example, if you go from a 3 nanometer to 2 nanometer, so we want to do a test chip, a test design. But for a real design, that when you go to work, usually you work on real design, you're just going to solve the real issue. Okay, real issue that design has because the congestion is going to be vary from design to design. Okay, vary from floor plan to floor plan. So you just have to fix the congestion in what you see in your real design that you see. Okay, so the questions is which cells do we apply cells padding techniques, sir? So that depends. You have to analyze the congestions. Okay, so it may be if you notice if the congestion around that one particular cell, so like a flip flop, a scan flip flop with 8 different pins. So if you just go to a different congestion, if you notice that cell has the congestion, that particular type cell have congestion everywhere to the left of it, then that's the cell that you apply cell padding for. So it depends on the congestion. That's why you have to understand the congestion and what it is before you apply the techniques. Okay, so this is not a particular cell type, but it usually tend to be the cells with high pin counts. Okay, so hopefully that answered the question on which cell type, which cells.
Complex cells are exclusive OR, exclusive NOR, those type of cells that really small but many pins.
Yes,
So,
usually it's on the high pin counts.
right.
Okay, so the next question, that's not question, that's from Ting. Yeah, so it's the same thing what Ting I said. Okay, thank you, Ting.
Yeah, and sometimes you say, just do the max placement density in certain area, and that might do the job as well. So cell padding is not the only weapon, right? So you will try and sometimes it's design dependent, and you try different techniques and you see at the end what gives you the best results. So if you say you try cell padding and you close timing and you analyze area and power, and then you try say max placement density in certain local area, and you go through your flow and you close timing and you compare the power and area. So sometimes you have to do those kind of try and error before you pick the best solution, right?
Hey, but did you cover a technique when
Ting, I think we just lost you. Can you type it in? Since your internet's not good, can you type it in? Finish your sentence.
I don't think you can hear me.
No, yeah, we got cut. I can hear you now. We got cut out earlier. Go ahead.
Okay. So usually, there's a technique that you can create, let's say, a certain blockages, or placement guide for a certain hierarchy in your design, right? You don't have to, if you have a
Yeah, we just lost you, Ting. Yeah, so Ting was talking about is you if you know the certain you can do a hierarchy related to your net list. You can set a density screens per module. Okay, so that's what he's talking about. Is that you do it if you know certain module has hydrogen pin count, and you can look at the placement if it's placed per groups, and you can set density screen based on that and limited the number of limited the density in that area. Yep.
Yeah, so I think what Tian might be referring to is that if you have, say, a very high speed block, and you know the hierarchy, say a DSP block, right? And you know the hierarchical name of that, you can say, what is doing some target density on that block. So you don't have to physically draw it, but
Right.
you can apply to a functional block. I think that's what he
Yeah,
trying to
so
say.
per module based density,
Yeah,
yes.
yeah.
Yep. Yep.
Another question from Wing Lemon, is there a case where we fix the congestion and you will see a problem somewhere else about that?
Sure. Of course. It's just a lot sometime there it's like a balloon, right? You push it here and it'll show up somewhere else. It has to go somewhere else. Of course. There'll be some cases like that. Right. And if you keep fixing it, keep showing up elsewhere, then you really have either floor planning issues um or your yeah or your related. So it's those fixes may not those so basically that's a more severe congestion. So by different strategy, and you're not fixing it, you may have to look at your re-examine your floor plans or your strategy and things like that.
So you might have you have to ask for bigger die size
Right.
because you
Yeah.
can because after everything you tried, there's nothing will solve your problem. Then you might have to ask for die size increase. That happens a lot of times, or sometimes you ask for additional routing layer. So just that but the difference between a PD, a physical designer, and a good physical designer is all in the result, right? If you're good enough, you can do with a die size, but but if you don't understand everything, you might have to ask for bigger die size. That in some cases not necessary. In some cases, is unavoidable. So that's something that. So if there's one design and one person, one designer can do it within the resource he or she has versus the other person who doesn't know deeply enough, the other person might have to have a worse design, meaning by having bigger die size, right, to solve the problems.
Yeah,
So
so before you go in to ask for more metal layers or die size increase, you better have exhaustively exercised all your strategy and have data to show, because they're going to ask you the data when you go up to management and ask for, because that's a huge into the cost cutting and affect a lot of things. So you want to make sure you try all your strategy, you have all your data to show before you go in and ask for things like that. Okay.
good point, because you don't want to ask for more and then there's another designer that can do the job with the same area. Then you don't want that to happen,
Yeah.
right?
So make sure you have all your data back up to show, yeah, this is the reason, and you exhaustively try all your different strategy, because usually management will ask for data to back it up. Okay. Any more questions or about congestions? Okay. All right. So let's move on to. Okay. So we already gone through this. I will back up. Okay, so at the inner placement, what do we expect to get out of it? Here I put down optimize net list, optimize def, time report, power report, congestion maps. So what I mean by optimize net list and def, basically, so these optimize mean that you meet timing, you meet all the requirements that the placements is it requires, right? You timing, of course, out of placement, you only care about setup timing, right? There's no hold time. We haven't talked about that. And you know make sure that you meet your power numbers, and of course you meet your congestions. The congestion map basically make sure that it is controllable. It's under control, meaning that the design is routable. So usually what happened there in the real design, you just save a DB placement. I think you guys gone through the first lab. We call it place.db. Just save the DB. It contains all the information there already, but in terms of to move on the next step. But things that you want to look at is reporting these maps, right? You want take a look at these things, to make sure. Actually, that's going to be the next topic. Okay, so how to review and qualify placement results. So first thing is timing, no or minor timing violations. So this is the timing summary out of placement, right? So make sure that the WNS, TNS that you've learned, make sure it's a positive slack. A negative slack, meaning there's timing violations, right? So if it's like 1 nanosecond, 1 picosecond or 5 picosecond, that's minor timing. It's okay. It's that's closable. If something like 1 nanosecond, then you have the issue. You can go back and look. But what I mean is minor, it is a few picosecond within, easier to fix later on. No problem. DOV should be clean except on the clock nets because we haven't touched the clock nets. So DRVs, we learn about max fan out, max cap, max transition. So here, you can see that there are 8 nets left. These are actually the clock nets. Okay, so we define there's 8 different clock nets. So there's DRVs on there. After CTS, you should see all these should be clean. Okay, so the other thing is make sure there should be no cell overlaps. Because I know sometime there's occasionally what happened when you do a place op, you add additional cells, and sometimes there are cells that are not placed correctly. You have to make sure they're clean and do an incremental ops, incremental placement. So make sure there's no cell overlap or no unplaced cells. So just do a quick check place. It'll tell you if there are issue. It'll say cell overlaps or cell unplaced, something like in the summary file. So these are the built-in command that will help you to do some of this. And most importantly, a routable design, minimum congestions. Like we talk about the overflow and the hotspot, right? So make sure these are these numbers here. These are the numbers, and also look at the maps. Okay, so but it should be corresponding to another. But if there's some numbers here there's some numbers, you need to look at the map to see where they are and whether it's under control, fixable or not. And hotspot score. And then your power requirement. So that's the other thing. In low power design, these are very important. Okay, so make sure you do report powers, and at this stage, just make sure that you within the meet the requirement with the range that you need. Okay, so we saw these report before, the internal switching leakage and total power. So in the last, I think in the last lecture, we talked about this. So you guys should be, this should be not foreign to you. Okay, so in summary, so to make sure there's no no or minor time violation. DAV should be clean except on clock nets. All cells should be legalized. Router design, meet power constraints. Daniel and Phil, anything else you guys want to add?
Yeah, you might want to re-mention why DRV is important in terms of extrapolation and interpolation.
You can go ahead and Phil. You can go ahead and talk what you wanted to talk about interpolation, extrapolation. Go ahead.
Yeah, so as you know, timing, right? Timing, when you analyze timing in here, you let me see if I can annotate. You usually have a lookup table with a cap and with the slew rate, right? And you have data, the delays in between a range of slew rate and range of caps, right? So if you have a table in here, anything, if you have caps in within the range of min and max in terms of characterization, or the slew rate min and max in terms of characterization, you have this table. If the caps are in between these values, or the slew rate in between these values, you're okay in terms of what we call interpolation, meaning within. But if your cap is outside, like bigger than maximum, or slew rate bigger than maximum or smaller than minimum, then you extrapolate, meaning this data is not fair. They calculate it from the data you have inside here. So say if you have two data here in between two caps, uh, uh, and these are two different numbers, say 1 and 2. If you have caps in between, you can interpolate, and this one can be 1.5. But if you have a data out here outside of the extra, because of non-linearity of the transistors, you cannot just do a K factor and multiply the delay by a certain percentage. So when you're outside of this, your delay, calculated delay, is way can be very inaccurate. So that's why you want max cap to be really and max transition to be within the library limits. Usually the library has these max cap and max transition inside the .lib files, but you have this additional max cap and max transition for your whole design for different purposes, and that will be related to signal integrity and everything. So maybe Tian can cover later, but I do want to make sure that the max cap and max transition built in the .lib is for this purpose, for accuracy. So what you want to review on your timing the final is this term extrapolation, right? Extrapolation. If you're in your report you see this word, then you want to get rid of this. This is a no-no. Your timing is not accurate because of that. So
Yeah. The square, that range you're talking about, and Phil talking about. So in a given technology, those are the range they characterize. So those data within that range are accurate. So it's far outside that range, they extrapolate. Okay. So within that range, that square that Phil was showing, that's sort of pre-characterized for that particular technology.
so when you do timing sign off and you have extrapolation, that means that you're asking for trouble. Your silicon might not work. Right? So
Yeah,
it's
I think
critically
that's,
important. Right?
yeah, I think that's toward the NSA. Yeah. Okay, so I think that's take us to the end of placement. We're gonna go to the labs. Okay, hold on there. Can you say regarding the DRV? To be honest, I'm not clear all about the buffer features. I know the buffers are used to drive signal to minimize the delay, but I don't know how they can do that. I know buffer are used to drive the minimum delay. I don't know that. What is the drive string buffer as X2, X3 in delay calculation? How does drive string affect the output of loading and max fan out? it's not a stupid question. Actually, can you ask a good questions. So let me see, and I can go back and annotate. So first of all, the DRV. So for example, just talking about max fan out, right? Actually, let me go back to the max. I have a slide on max fan out. Okay, so for example here, right? This is this buffering. So for example, max fan out. So let's say you have if this is a fan out of, let's see, this is cloning or this is fixing technology, adding from, okay. So this may not be good. Let's say if you have buffer here, right? It's going to drive. This is not a good design. Where's buffering? Let me just draw it. Oh, where's the annotation? Okay, so let's say if you have let's say each of these are fan out, right? And you have buffer driving here. And 1, 2, 3, 4, 5. Let's say if the max fan out limited to you to 3, right? 3. Then this is max fan out 5. This is too many, right? So you gotta add a buffer to limit the fan out of this guy. So you okay, so you might split it up to 3. Insert the buffers here to break up the fan out, to split this up. So that's to break up the fan out. In terms of the cap, the max cap. So you have a driving cell this long, and the cap, the longer the wire, the more caps, right? The cap increase. So if let's say this cap here is 0.08, right? But your max cap limit is 0.05. Then you insert buffer in the middle here. You break this cap in half, 0.04 each. Therefore, you break up the caps. Therefore, you meet you meet the max cap, right? You break it in half. That's how it's done, right? So you basically break the wire in half and divide the caps and divide it between the two, right? So that's and then in terms of the X2 string, 5 string, because remember 2x, 3x basically is the size of the transistor, right? The doping. So the bigger transistor can be able to drive. If you look at the library, so for example, let's say the X buffers, this one is X2, it can only drive 0.05, right? 0.05, but the bigger for X4 it can drive 0.08, right? So if this is 0.08, let's say 0.08, then you change this out to the 4x, then it can drive 408, then you meet the timing. It's just like a bigger guy. For example, a bigger guy can carry more than a little guy. Kind of like that, right? So the X2, X4 basically mean that the transistors are much bigger. It can drive, it can tolerate more, it can drive more. So that's how if you swap it out, the buffer out, and then you can meet the DRV. Does that make sense? Can you hopefully that answer your question? Hopefully that make it a little bit clear for you. Okay, I got a thumb up, so I assume that's understood.
So could you illustrate the buffer characterizations?
Oh, okay. Let me. Okay, let me. I can't get. Hold on. Let me get rid of my pen to go back. Okay, so the buffer characterization, I guess the curve, in terms of the drive string, if it's X1 here, I don't know what you mean X2 here, and this is the drive. I don't know what he meant by characterization.
I can try to answer. Yeah, I think what Kan Jung is confused about is that how buffers can fix the DRV, I guess. So you already explained it, but let me try a little bit more. Say he relate to X2, X4, and you try to explain it already, but let me see. So if you have an X2, yeah, you want to
Let me
clear?
clear this up. Hold on. Let me clear this up. Let me go to another slide so it clear up.
No, it won't. Let me clear for you. I clear
Okay.
outright.
There we
Okay.
go.
Right. So if you have an X2, right, we talk about the characterization being the slew and the cap, right? So if you have a cap of X2, maybe the max cap, like Bat was saying, say 0.04 or from 0.4 femtofarad is a max. I forgot what would be meaningful, but say 0.4 femtofarad, maybe 4 femtofarad is the max it can drive. So if you have a load, here of 8 femtofarad, right? Then you use this X2 to drive it. Then you extrapolate. So you swap this one to X4, and then X4 in the table, it's a max cap can be, like 10, right? 10 femtofarad. So if X4 is 10 and you're driving 8, then you use X4. You're not extrapolating when you drive an 8. I think it's just that's how it related to characterization in terms of the table. I hope that additional thing will help you figure out how buffers can do that. Right? So.
Yes. So the characterization data is done by the cell library team. So there is a separate library team that actually build library and characterize the library for they do characterization for these things. So they have these curves and things like that that to show you exactly the different drive string, how it actually tolerate the fan out and the cap and things like that. Okay, I think we hopefully answer your question.
Yeah. Let's move.
If it
Let's
does
move on.
not,
Yeah, let's move on to the lab. I
yeah,
think we
if it's
only have
not, email me and I'll get some of the data back to you. Some of the charts or more details. Okay, can you? You email me or Phil, either one of us, or thing. We can get with you later on to help you on this. But we need to get to the lab. Okay. So then here's the lab. It's all of the lab. Okay, so let me get rid of this. This is I think I saw a message saying that lab 6 not running. Actually, I just tested from the lab. It's fine. Okay, so I'm not sure that's maybe an issue because I actually just went and copied the lab over and make sure it run.
So when Gautam raised that, so perhaps they can get with you after the class.
Yes. So
Um, thi- I'm take a shift in Ho Chi Minh, and last yesterday all student we have encountered the same problem, like, and I think it in
Yeah.
the place that you have placed in.
Yeah, I think, but it's related to you being assessed. The data is referring to your home directory. Not all the student can see your home. That's a problem.
which lab? The lab 6 or lab 5?
Lab 6. So you go to lab 6, you go to DB, maybe data. Let me try to see.
Yeah. Yeah. I know. So I should write. Let me save it standalone DB, and then they can see it. Let me save it as a self. Yeah, because I see. Yeah, I know what I'm talking about. Yeah, they refer to my home directory because it's a DB. I copied over, correct?
Yeah. So it's easy to fix. So and now you can illustrate and you can fix afterwards. They should be able to be up and running shortly. Yeah.
Okay. Yeah, because I actually continued the DB from the last time I sourced it and referred to my home directory, correct? Yeah. Okay. So I'll fix it after this. Okay. So lab 6, once you get in there, this is the issue right here, the place out that. Okay. So let me go, let me go into this. This is, okay, let me get rid of this. I have too many. Okay, so in lab 6, you will read the place.db, which is previously done, or you can read your own place.db. So if you've gone to, you should read your own DB. Okay, so if you've gone to lab 5, you should save a DB called place.dat in your DB, wherever you run it, and read it from there instead of changing the directory, DB directory here. Just source it. So here's a better solution. You should use your own DB. Okay, so do this. Just change this DB to wherever, point it to your directory, okay? Point it to your directory, your DB directory. So after your lab 5, replace it with your DB, okay? Your path. Okay? So you should have saved the DB at the end of lab 5 called place.db. Use that one, okay? Instead of using this one. So that will solve your problem, okay? Just comment this one out. Okay, and source it so it return. And here I put in a couple of comments just for you guys to know. So remember in the previous lab, we set these analysis type to OCV and then CPR to both. Here's just a quick way to check to make sure that it's still sticking, right? It should when you save it in DB, all the settings should stick in the DB. You shouldn't have to reset it again. So just to show you a way to check that is still, this should be 45. Okay. So when you read it in, you should have your place DB here. Okay. And the next step is to run optimization. Right. So what this does is op design that's pre-CTS is telling us, okay, we're in placement, there's no hawk tree, and we're doing the setup. I think by default, you don't do setup, it does setup. So here I just explicitly say setup. And then this saying, okay, go ahead and generate a timing report. I think in the previous one, if you do without this, it generate in a generic report. So if you tell it where it is, it'll generate it in the report directory and tell it, okay, all the file will have the prefix step underscore op, in this case, place underscore op. All the file will have place underscore op and put in the directory. So it generate time report for you. So this take a little bit. So I already ran it in this DB here. It take probably about 10 minutes, or maybe 5-10 minutes. So I already ran it. So you just cut and paste this. And after that, I normally just do check planar check density. Here, you see it's 56%. Okay. Okay. And here I put yeah, so basically here I put a command run placement and preset ops at the same time. So instead of run place design and then op design, you can run place op design in one shot instead of 2-step. So basically I just command here. It's the same thing as run in the last lab, you run place op, place underscore design, it's place the design, and then here you run op design, which is do the preset optimization. You can do the same thing in Innovus by just doing place op design. Okay, both in the same step. Actually, in reality, we run them both. We run this command concurrently instead of 2. But to show you the placement, to demonstrate the placement, and then the pre-op, I ran it separately. Okay. Okay, so here I just wrote out a net list for you to take a look at. So if you write out a net list here, and you can take a look at the net list now. Let's see, what's this one? Yeah, so in the last one, we did the tie insertion and everything, right? So here you can take a look at, you can write out the net list and just take a look at it. There should be no one tick B0 here at all. Let me see if this. Oh, so this is actually has not had tight cell insertion. Come on back. So I don't know why I put it in there. Oh, this is before. Okay, this is before. Yeah. So this is before it doesn't have any ties. So I have one tick B0. So later on, you'll see you write out we have now one tick B0, one tick B1. So before tight cell insertion, it still has it. Okay. Okay, so we write it out. We see that there's no there are one tick B0 in design still. So the next step is after you run your timing op, right? Let me see if take a look at timing op before I go there. So we run timing op. So there is we call place op, right? So let's take a look at the place op timing estimation. What's the issue? Okay, I have to be outside of Innova. Sorry. So after you run place op, so this is let's look at the lab instruction, right? You source this, you get DB. So after you run this, right? This is take a look at the timing report. So here you can see the timing place that we clean everything up pretty much. You clean all the setup times, but the DRV still clean up, okay, except the clock nets. So this is a good timing report. Okay, so log file. Okay, so here I have you look at the log file. So initially you can see how many violations are left here before it's actually run timing ops, right? It's so you can see there's minus 3 nanosecond WNS and 5,000 something time TNS, and then there's 5,942 violation path. Okay, out of 12,000. So this is initially, so the log file has this information in it. And then you can look at, it does high fan out synthesis, the DRV, and all that stuff, all the steps that we talk about in during the ops, right? So you can see it does it all in the global routes. So look at your log file and search for these keywords. You can see what's you understand what's happening in there. Okay. So here I go over the directory structure, the timing, the report directory structures. Let me go there. Okay, so here's all the place op, right? This is all the different timing path groups. These are the path group. Remember we set path group, and you can see mem to reg, res to reg. These are detail report. These are summary. So if you come in here and if there are timing violation in reg to reg, okay, and you know exactly you want to find out. This is I'm sorry, this is after placement. Okay, so we can take a look at the red to red placement, right? You can see you should be able to see the detail of these violations in the place. This is the place. So let's look at the place. The place res to reg. Do we have it here? Where's place res to reg? Oh, here we go. There. So you can see the corresponding, right? Minus 3.957. And it's a setup check. It's a res to reg, right? And they tell you what clock, what's the clock group. So in this case, you can see there's no clock, there's zero delay clock. There's no clock tree in here. So this is the top summary. And then you can go down here. These are the detail timing. So here is the this is the launch clock, right? It go to this is the clock gating cell, and it hit the first flop. Okay, and then these are the what we call the launch clock timing path. It's all zero, so no delay here. So okay, you can see no delay. And then this is the data path, which is the rest to rest, flop to flop, right? So we go through, AND NOR gate, and then it hit the next flop, right? So this is your data path, rest to rest. So it take this much time. And then at the end, this is the launch clock. I mean, the capture clock, sorry. This is the capture clock path. You can see it's 4 nanosecond period there, right? So, right. And so that's how you can tell what's going on with the timing, the detailed path analysis. Okay, so whichever timing group you have timing issue, you can go and look at the timing path group. But first, take a look at summary. Okay, and then okay, yeah, I talked about the pot. So you have positive slack, that means you meet timing. Timing is clean. Okay, I talked about this already, DRV. So at the in this, you can see the density, right? The placement density and the overflow. Okay, so these are the numbers. Okay, so we look at the rest of the time reports. Okay, we talk about these. Launch clock, data path, capture clock path. Okay, so check for plan density. Yeah, I think we did that right here. Check for density. Okay, core. Remember, core is including macro. Okay, we can do a quick check place. Okay, so there are 35,600 cells in here, and 4 fixed. These 4 is fixed. Fixed meaning so a placement there's fixed and there's place. When there's place, it means that it can't. Let me show you. If it's placed, that means the tool can move it for optimization. So let me show you real quick. So you can zoom in, just click on a cell and turn on the attribute. Okay, hit a Q, and then you see the attribute place or fixed. This should be fixed. So it's somewhere down here. I used to hit summary. So place status means it's been placed. That means the tool can move it. Okay. If you don't want a tool to move it, put a fixed status on it. Okay. Just edit. It's a little slow, but you should be able to edit this and fix it and hit update. The four fix is the macro, the memory. Usually those should be fixed. So this guy, hit a Q on it. It should be has fixed status. There you go. Place fixed status. Right. So those four reporting in placement, checks placement is the full memory. Okay, so what in one of my runs it show there's eight overlap cells. Okay, so in this run it didn't have it, but the run that I did it has 8. So I show you how in the lab in case you have it, you can how to fix it. You run an increment replacement, okay, to fix it. So okay, so I don't have it here, but this is called violation browser here. If you do, it will show up here. Okay, this looks so it will show up here as overlap, like here, like I show you on the lab. It's a little small. Let me open it. So when you check place, it show 8-inch overlap here, and you can actually click on it, and it'll bring you to in the floor plan here in the physical view. It'll bring you to that instance. So once I click this, it brings me to this. So show you there's overlap right here. You make sure you turn off all the net, right? You see these 2 overlap cells. So that can happen after a place out anytime that the tool add cells in. So that can happen. So in this run that I did for the labs, it has it. So I went ahead and show you guys how to do it here. but in this run I didn't have it. Okay, so let me back up. So to fix it, you do a place detail.eco. Okay, so you want to know what that does? You can do a man on it, right? So a little slow here. You can do a man, place, detail. Okay, correct any flaw cell location, report correction, or report and instant overlap problem, right? So you can do area or per area, or you can do the entire design. Okay, on a big design, we usually do it per instance. You just per instance, like you have a list of 10 instances. I just give a list and just only place the instance. The runtime is much quicker. But this design is so small, I just do a place that is so true, and it does fix anything in there. Okay, or you can do per area, right? So this is how you can tell and get the syntax. Okay. So for the lab, if you know the cell, you can follow the instruction and do place detail that's ISO that's instance, and it'll fix that problem. So here I just have you guys do that's ISO true, and you can see the log file here. Before we had 8 instance overlap, right? So I ran the incremental ISO placement. It fixed it, right? So there's no more overlap. Just it moved 4 instances, so there were 4 instances. So a 4 instant overlap report is 8 because it's total 8. 4 overlap, it moved 4 out, so it fixes 4. So it's total 8 instant. That's the way it reported. So if you have 1 overlap, it's reported as 2 because 2 cells. So in this case, it moved 4 away, and there's no more overlap. Okay, and it tell you how far the distance moved, what cells, and so on here too. Right. So in your lab, if you run have to have after you do a check place and it has overlap cells, and you can do place there. That's also true. You do this step. If you don't have it, then don't worry. Skip to the next step. You can run it, but it won't fix anything. It doesn't do anything. I mean, it doesn't move anything because you have no. Okay, so you do check place against all clean. Okay, add tie cell. Let's go ahead and do the add tie cell portion. So I'm going to go back to my script. What happened? Go. Okay, so did I add that cell here? Okay, so remember ties that have constraints, right? So here I'm telling it to do max fan out of 10, and then distance 20. You can experiment, try different numbers you like. For this exercise, it doesn't really matter at this point. Just rather other than understand how that tie cell being added and how the constraint affects. So I'm gonna go ahead and set this. So our tie cells, if you don't know what the name of this, you can do this. You can do but usually you work at technology, you should know what the name. So if you don't know, you can do get live cells. Oh, hit tabs, and then just do a star tie, and it'll come back with the name of it or exact name. And here this is the library name. This is cell name. So all you specify tile and tile here. That's how I know what the name of it is. Okay. So I'm gonna go ahead and do this. If you do it again, it just overrides. So if you do the same command again, it override the previous setting. It will retain this setting, the last setting. So now I can just do add tie cell. Okay, so it said it add a total 409 cells. And let's see. And I put in a script. We want to know where it is. So Now let's do a quick check place to see if they actually have any issue with placement. So it's clean again, no overlaps. Let's look at where it is. Okay, so here, notice here, if there's overlap, I do an if here, 0 meaning it's not going to execute this script. You can change to a 1 if you want to run the place ECO, detail ECO increment placement, change to a 1, and it should run it, or you just cut paste this portion. Okay, so I want to know where the tie cells are. So let's just select everything, and then select both high and high low. So this is getDB instant if the dot name is tie high and tie low. Okay, so it'll get both of them selected for us in the GUI. Okay, I'm gonna go ahead and turn these are the false violations on the Power Grid the PG. So I'm go ahead and turn that off for now. So you can see the tie cells are here. You may ask why is it here, not over here. It's because the netlist, remember, it dictate where the ties are being added. So these are the cells that has one tick B0 and one tick B1. So it added right next to this guy, right? So this tie cell here, added, there's 2 fan out. This one had to be 1. We say maximum of 20, but if it doesn't need that, it added 1 everywhere. See, you can see here. So mainly flops. So you can zoom in and see. Okay.
So time check, you have about 2 minutes. There's one question.
Oh, okay. One question. Okay, network is not stable. Keep being locked out. Sorry, teacher. Wait, can you?
Not one before that.
Can you do one place detail instant as how to use for command? Okay, so yeah, let me do this. I am go ahead.
You do right, yeah.
Okay, so I'm gonna go ahead and move this cell to overlap this guy, right? So it's clearly overlapped. So I'm gonna go and check. Do a check split. I should see one cell. It should report. Right? So let's zoom in to this guy. Right, here's check over in 2 instance. Right, you click on this guy, it should point to this. Okay, so I'm going to turn up select violation. I'm going to select this cell first. I mean, I know the instance name already, so I can just do Q on this one and get the instant name out of it. Okay, so this is the name. This is the instant name, right? I'm going to copy it and just do place, detail, dash ECO, true, dash instance, and then that instant name. Okay, and it should move that cell. So you can see it said move 1 cell, and go to the GUI. It move it, right? Okay.
Okay,
so,
there's another question. Yeah. Nguyễn Văn Dương asks, could you show me how to delete the spare cell module as I create it in a wrong way and I cannot delete it? I need to create a new one instead.
Okay. Okay, so you want to delete it? All right, so when you create this spare cell module, okay, you have the name of it, right? It's module, so it's the name of it. You can do there's a command called ECO or delete instance, I believe, or delete module, delete instance. Yeah, so the delete instance, is there yeah, so you can delete instance. You can do a manual delete instance, and you name all the spare cell. Grab all the spare cell and spare and just delete it. Okay. So you can do a wildcard on it. So here's the instance, or you can do a module. If it's a module spare score something, just do a delete instant dash module, and it'll delete it out of the design. Okay. So I think it's called spare. When you create spare module, it will say spare module one underscore whatever. You do a module star and like this, so you can do delete instant dash module spare
Yeah, right.
star, and you'll get rid of all your spare module.
Yeah,
Okay.
and I would caution about deleting something here. I would propose that you go back to the flow and reload the data and then rerun instead of deleting in the database. Sometimes if you make mistake, you can delete the wrong one. So
Right. Yeah.
yeah.
You have to know what you're deleting, because deleting, you leave those nets, the spare cell. If you have connector or anything, you delete it. It's okay. But if the real instance you delete it, there's net dangling, and you may have some functionality issue. You have to know exactly what you're doing. But spare cell, you haven't connected anything, then you can just get rid of it.
Yeah, you save very often and then you go back and reread the last database and then rerun the scripts
Yeah.
instead
So
of deleting.
then you ask, well, tab cells are necessary to be added in design, but this lab, I don't see any tab cell. Can you explain more about it? Yeah, tab cells basically is for latch up, right? It's you there's a rule that you specify every so often in the design. You do that during placement. You spread it out per column per design rules. In this, we don't have any in our lab. We don't have any tab cell, but you place it, you pre-place it just like according to the design rule, usually in a vertical column with certain distance at the design guidelines that the technology tell you. You place it in vertical. So those are pre-placed design. It's not going to be placed during the placement. Those happen in floor planning stage. Those are
Yeah,
pre-placed
and
design.
right. And you use Tickle script to do it, and then after that you do a fix so that yeah, they
That's right.
won't be removed, right?
Spares,
So
we didn't, yeah, those tab cell were also boundary cells also, right? We usually place
yeah.
them on the boundary cells too. Yep. Yeah. Yeah, we didn't have time to cover the details on all those things, all those cells, but they're pre-placed cells. Okay, is there any way to override the module instead? Unfortunately, I'm not aware of any way to override rather than delete it or go back to reload the module. I have never override a module. Phil thing, you guys can, what's your
No,
guys' experience?
no, not recommended. And there's no overriding, just deleting and adding. But like I said, I recommend just go back and reload and rerun.
So Leighton Jung said, I don't know. I want to know why optimization still allow overlapping. I thought not overlap should be a constraint. Yeah, so during placement, the tool should not overlap, but sometime what happened is at the end it just there's a few cell left. This is the algorithm of the tool, so you gotta help the tool at the end. So um, I don't know the algorithm internally how that worked, but sometimes you do have it's a seeding, but and yet sometimes it exhausts. I can't really truly answer that question. Phil, do you know?
Yeah. So similarly to DRC, right? But in theory, it should fix all the DRCs, but
Well,
for
sometimes.
difficult spot, it doesn't. So that's why you do incremental, you do focus, and you do local fixes and everything. So it's a tool limitation when you throw it at so many things. It will go through iterations after iterations to fix everything, but after it maximizes the number of iterations. It will leave something undone, and you go in and you zoom in and you help the tool a little bit. So it's normal, right?
Yeah, that's why they have those increment placement, incremental
Yeah.
place to fix these things for you. Okay. Okay. So we probably don't have time to rest the lab, but the lab is pretty much self-explained. You follow step by step here. Okay. So I have one step I had you guys is pretty much explained here. And take a look at the. So if you go through after you do its type insertion, you can see right at the net list. You can see those cells be the one tick B0 are gone. Should be replaced with the type tie high and tie low. Okay, yeah, we talk about that. And then, yeah, so you can take a look at the spare cells, right? I mean, the tie cells, similar to the spare cell, same thing. I have the script in there that you can take a look at it. Oh, we already look at it, right? Similarly, you go through the same thing as tie cell. In the spare cell, you can see the cluster here. We can quickly talk about the spare cell. Okay, so to create a spare cell module, right? We call it spare underscore on the prefix. So it depends on, it may add a lot. I don't know how many modules. It depends on the size of your core, because here we tell it to place it according to the size. So 50 micron apart, X to Y direction, and then 10 micron away from the boundary, right? So based on that, it will create and place the spare cell accordingly. So it may be 100 module or so on,
So
right?
you 7 minute over.
Yeah. So yeah. So I just want to quickly show them the. So here's the highlight. So I just told to highlight the spare cell, right? You can zoom in and see this is a different cluster here, right? So you can do that. So you follow lab instruction is pretty much what I just show you guys along the lab. I think in here, congestion is okay. So congestion is one important thing. So let me show you how to turn on congestion. That's the important part. Okay. So for congestion, you need to go into the overlay section here. Okay, so where it say congestion, expand it, route congestion right here. Click it, and then up here on the upper left, there's this little icon. Click on it. Okay, so now I come up with congestion, right? So the default diamond, and then you can see the different colors, right? So you want both congestion here, so hit apply, right? In this case, we have no congestion at all in this lab. So I want to show you how to, this go away. If this go away, just hit this thing, make it stay. There's no congestion in the lab. I had you guys change the congestion, the routing, the global routings, right? I believe I had you guys change the global routing to make sure it changed to 3 layers. Okay, so here, layer, I show you how to change it to 3 layers, right? So you can do set DB global route 3. Let me show you congestion real quick. So for the purpose, just limit the meta to 3, and you should see congestions. Okay, here. So I'm going to change it and do a global route. So basically tell it, okay, use only 3 layers, and then that make congestion show up. So here you can see now there is, where is the global? There is congestion right here, right? So we should be able to see it in here. If we click on this. So now you see congestion, right? So you can zoom in this area. You can see what we saw in the lab, right? You can see his 1 to 18. Okay. So follow instruction to play with congestion, you know, on this. Okay, I think that's if you follow instruction, you don't understand something, feel free to ping me, but it should be self-explained. So for those who use your own place the DB, if you don't have it, let me know, okay? But use your own, okay, to move on from this.
Yeah, so if you can fix the path to the libraries and all immediately after this, so if they want to try, they you have a
Yeah,
won't
but
have a problem.
yeah, use your own, you first, but I'll fix it a little bit out here. Okay, that's all. Sorry, we ran 10 minutes over, but I think it's critical that I show you how to use the congestion map here. Okay, that's all for now. So next week we will start talk about clock tree synthesis. I think I'm not sure what. Somebody, one of my buddies, told me about what to call it in Vietnamese. Yeah, cây đồng hồ or something like that, right? Clock tree synthesis. But next week we'll dive into clock tree synthesis. All right, thank you all.
Recording stopped.
All right, thank you.
Okay, bye.
See you next week.